Thank you very much. Biology, technology, future. These are the three words that buzz around in current days because biology has long moved on from a simply observing and describing science to an engineering one. Researchers are pushing towards so-called intelligent materials, towards growing materials, biofabrication. Very tempting thoughts from my point of view as a designer. But what does it actually mean to design nature? Especially when you think of methods that have recently been developed that allow to change DNA in such a way that it is possible, or that it is not distinguishable anymore from natural mutation. Genetic manipulation has not just become very simple, it has also become very cheap. So it's not a question anymore if we want to stop biotechnology, it is happening. It is more a question, where does it lead to? And actually I prefer the question, where do we want it to lead to? This very fundamental question, I believe, urges to be discussed not just by experts, but in multidisciplinary settings and by the public, by you and me. In order to find a way, or to give our evolution a way out of this very, very chaotic and also unforeseeable situation we're in now. I believe design could and maybe also should play an important role here. By collaborating with natural science researchers doing cutting-edge research, design actually offers the possibility to create and explore all kinds of possibilities and not just go in one direction from the very start, but to try them all and really create manifold artifacts and scenarios which I believe are crucial for constructive discussion on how we want to live tomorrow. Well, but where to start? Let me introduce you to a very particular bacterium. Even though bacteria might not sound too promising to you, they're not all as bad as one might think. This one is actually quite a good one. It's called Bacillus pasteur and it lives all around you in your direct surrounding in soil. As you can see on this image, it only measures 1/1000th of a millimeter. But despite its very small size, these bacteria live and work in colonies and are thereby able to produce materials far bigger than their own size. Here you see a bacterium sitting on a sphere of calcium carbonate that it produced itself, or with his buddies. Calcium carbonate, a mineral, or to be more precisely a biomineral, because it was produced by an organism in this case, just like our bones and our teeth, which are produced by our cells, more or less the same size as these bacteria. The interesting thing about biominerals is that they're being produced at room temperature, whereas industry often needs hundreds or even 1,000 degrees Celsius to do so. So the question is, can we harness this potential? Can we make use of it for industrial applications? And what would that mean for them? What would that mean for us, for everyday life? In order to find out, we teamed up with Felipe Natalio's research lab from the Martin Luther University here in Halle. And together we created various and a wide range of scenarios. What would that mean? And today I'm going to show you a few of them, hoping they will raise discussion. The first scenario deals with the question, what if these bacteria that I just introduced you to could turn chaff, crop waste, into cement? But first of all, what is cement and why are we thinking about making cement using biology? Cement alone is calcium oxide and silica that hardens when mixed with water. The problem, though, lies in its production, because the production of 1 kilogram of cement also produces 1 kilogram of carbon dioxide. This is why 5% of the overall industrial carbon dioxide emissions derive from the cement industry. So it's kind of obvious it needs to search for alternatives. Two students of mine, Tony Bayer and Muyu Chao, suggest an alternative in chaff, crop waste. Because on the one hand, there's loads of it and it's hardly being used. And on the other hand, because rice husks, for example, contain up to 30% of their weight in silica. So what if we combined our bacteria as a source of calcium with the husks as a source of silica to produce a kind of biocement? And this is Tony and Muyu's answer. They created a setup that allows people everywhere in the world where there is crop waste, and this is kind of everywhere, to first grind the crop waste, grind the chaff, then fill it into a mold, a form of any desired shape. In this case, they used 3 different iconic bowl shapes to represent the different origins of the chaff. And after closing the mold, then one fills in a liquid media, a nutrient media also containing the bacteria. And actually this liquid media can be made out of whey, the leftovers from the cheese production, because whey contains just the right nutrients for the bacteria to live off, as well as loads of calcium ions. And then after that, one just has to wait until the bacteria have produced the biocement using the silica from the husks, and thereby gluing the husks together to form a solid. So this concept proposes a kind of fabrication involving the people, a bit like craft beer, but with bacteria instead of yeast. It also shows a completely different idea of making cement, probably also leading to completely different products made out of cement, but it also questions our relationship to these kind of 24/7 workers in our direct surrounding, working for us especially. But this is not all. Let me give you another example dealing with a different question. The question, what if our food is not sufficient in nutrients anymore? Actually, we live in a world where 50% of our food is engineered in one way or the other, either by pre-processing, as I would call it, involving biotechnology and gene manipulation, or by post-processing, usually using chemical methods. Take low-fat milk, for example. It indeed contains very little fat, but the process to remove the fat also removes other components, such as vitamins. So most engineered food actually lacks nutrients which are important for our body. One example of a consequence is osteoporosis. Annually, 8.9 million fractures happen worldwide due to osteoporosis. This makes one osteoporotic fracture every 3 seconds. The main reason for osteoporosis is a lack of calcium and strontium. This people try to compensate by taking pills. But could biotechnology maybe help us to find an alternative to taking pills? Andreas Wagner, a student of mine, asked himself, what if everyday medicine was supplied by everyday objects? So he developed a concept where our bacteria are used to coat tableware with layers of calcium, magnesium, and strontium. The bacteria are so versatile that they're able to coat all kinds of materials, such as wood, metal, plastics, and even glass, if it's slightly sanded. This is the finding by Felipe's research lab that we collaborated with, and based on this finding, Andreas created a kind of dishwasher, if you want, with an added function, the bacterial coating. This bacterial coating is then being washed off while eating from acidic food and acidic liquids, just in the right amount as needed. So all in all, I think you will agree that this concept is quite sound and involves beautiful objects and also describes a nice everyday life without having to worry about empty food that doesn't feed us anymore. But to be honest, doesn't it also leave a bitter aftertaste? Do we not rather want proper food again? And how do we feel about functional bacteria in our dishwasher? But remember, these projects are about opening a discussion, in this case on engineered food, on the quality of food, the quality of eating, and also on the possibility of growing your own medicine at home. And maybe also on to what extent we can rely on biotechnology. And this, I believe, is what the project does very well. The two projects I'm going to show you now deal with the same question, with the question, what if we could grow materials? If I think of bacteria that are able to coat materials with calcium carbonate, what these bacteria actually can do, I immediately think of nacre. Nacre, a material that consists of many layers of calcium carbonate, but also a material that is known to be 3,000 times stronger than its original component, the inorganic component, the calcium carbonate itself. And this is due to its very particular composite structure, also involving 5% of organic components. But nacre grows in shell shapes, which are not very useful for us. So the question could be, what if we could grow nacre in different shapes and structures, in desired shapes and structures? Tom Bade, another student of mine, created the vision if we could grow nacre composite layers on textiles, coating each yarn with these particular layers of calcium carbonate and the organic components so that they eventually grow together to form a very lightweight but very strong at the same time object, as you saw here in the animation just now. So he developed a process how this could actually work. First, he creates a textile made of fibrin, a protein that silk mainly consists of, but also the protein that is one of the two organic main components nacre is made of. And this silk textile structure he puts into his machine as a kind of starting structure, and the machine pumps in a certain rhythm 3 different liquids through the textile. The first one, the liquid media with the nutrients and the bacteria to coat the textile structure with calcium carbonate, and then layers follow of fibrin again and also chitin, the other organic components. And after many cycles, the textile structure is actually developed and has produced a construction which is very lightweight but super strong at the same time. So this machine, of course, demonstrates the possibility and to a certain extent even the feasibility of growing this kind of smart material. But it also questions how easy and maybe also how difficult it is to do so, especially without reprogramming the DNA of an organism. The other example dealing with the same question doesn't involve nacre, but involves mycelium, growing in symbiosis with our bacteria, as we started calling them after a while. This idea, or rather this proposition by Ruben Strahl, another student, is that mycelium, which is usually a chitin, a fibrous chitin structure growing in soil, could also grow in air and then in any kind of structure as we wanted, if, on the one hand, the nutrients were supplied as a fog, and if, on the other hand, these very fine chitin fibers were being calcified while growing by the bacteria living in symbiosis with the mycelium in order to give it the right stability. If that was possible, then we could actually control this growth parametrically by the intensity and also the direction of the fog. Even though he actually did achieve very first proofs of symbiotically grown calcified mycelium, this stool is of course a foam model. But it still shows very well what could be possible with a CNC-controlled growth of natural materials. It could lead to an extremely versatile production and also to products that are not just biodegradable, but highly adaptive. Does that sound plausible to you? Starting from a very small bacterium that is able to produce biominerals, these were just a few examples of what could be possible when using them in industrial context. But besides their scientific research impact these could and probably have, They mainly demonstrate or question on how we want to live tomorrow. And more importantly, actually, they help us to form an opinion on what is not just possible, but what is also plausible. Because I think 1 + 1 should be 3 in this case. If we design nature, what we actually already do, biotechnology should be more than just biological and technological. The 3 represents the human aspect, the sustainability aspect, the added value. Thank you.